try. This is a weird idea I had, which is to document some of my musings about physics and math. In particular, in physics right now, we're doing rotation, and I've been quite interested in moments of inertia. So I thought I might try to derive the moment of inertia of a disk by myself, without any sort of help. Yeah, so let's take a look at the problem. Just saying there's probably way easier ways to do this, because this is just what I came up with. Just want to solve it, but I don't know, probably more clever ways. Anyway, it's quite simple actually. We have a disk here, it has some mass m, it has a radius r, and it's being rotated around this axis perpendicular to the ring, going through its center, L. Here's our coordinate system. We have x and y. Xy is perpendicular. Xy is the plane of the disk, and z is the z-axis is parallel, or is the axis of rotation L. All right. So the equation that we're going to use here is this equation, which is a small change in moment of inertia is r squared, where r is the distance to the axis from some point, times the differential in mass. All right. So we're going to call this region of the disk, infinitely small disk, infinitely thin disk, Q. So Q is the numbers, is the pairs x and y such that x squared plus y squared is smaller than or equal to r squared. Pretty simple. We're going to be integrating over this region to find the moment of inertia. So we know that moment of inertia is this, not too bad. We also know that our total mass is this. And one thing that's important here, because this is infinitely thin, we're not thinking about things in volumes. Our mass, our differential in mass is going to be proportional to the differential in area. So dm equals dA times c for some constant c. This constant, it's constant in the sense that it does not change in terms of where on the disk you are, right? And the way that we can find what c is we also know that this is just the area of the disk, which is pi r squared. Therefore, if we integrate both sides of this equation, we get this, which, if we replace this with m and this with pi r squared, we get, and then solving both sides, solving for c, sorry, we get m over pi r squared. So therefore we found that dm equals m over pi r squared, constant, times dA. All right. So now we can find I. So I equals integral over the region Q of dI. dI is r squared times dm. So that's r squared times, we found dm is m over pi times big R squared times dA. Now we're going to switch into polar coordinates to make things a little bit easier. We're integrating over a disk, so we're going to have 0, it's a complete circle, right? It's an arc, so we're going to have theta go from 0 to 2 pi, and we're going to have the radius r go from 0 to r, and then we have r squared, like the distance center, which is r, times m over pi r squared, times dA. Now, the Jacobian determinant of the transformation from rectangular coordinates to polar coordinates, of course, is going to be r, so it's going to be times r, dr, d theta. So this is our moment of inertia. And we can evaluate this. So we do the inner integral first. This is an r cubed cubic inside. So we're going to get integral 0 to 2 pi of m over 4 pi r squared times r to the 4, evaluated from r to 0 theta. 0 plugged into here just gives 0. So plugging in r, the r squared and r to the 4 cancel out to get r squared. So we get this. Now this is a constant with respect to theta, so that's just right. Now we plug in 2 pi to this, and then we plug in 0 into this, we just get 0. So that's m times r squared times 2 pi over 4 pi equals 1/2 m r squared. That is our I. Moment of inertia of a disk.